So we're going to continue discussing optimization, but we're going to consider a new problem, sort of a fun one. All right, so there's a river, okay? And there's a location someplace down the river on the other side. Maybe it's a camp or something that you would like to get to, okay? And then you have a starting point. So let's say you're starting right here. So you start right on the edge of the river here. Now let's talk about your options, okay? You're obviously going to have to get across the river and then down the other side of the river. So one thing you could do, if you wanted to, would be go straight across the river, right? And then when you get to the other side, go at a right angle down this side of the river to the camp. So that's a possibility. All right, so let me give you some information, okay? This is a long ways down. Let's pretend that's 5 miles down the side of the river. And let's pretend this river's pretty wide. It's 2 miles wide. That's pretty wide. Okay. So maybe you have a little rowboat or something. You're going to row straight across and then go down the river. All right. What are other options? Well, another option might be that you decide head straight from the starting point to the camp. So maybe it's going to get in the boat and paddle like that. Okay, so you might think, all right, well, if I want to get to that camp as quickly as possible, which is going to be the goal here is going to be what's the fastest or the least amount of time it's going to take me to get from the starting point to the camp. You might say, okay, I'm going to travel along that black path because that's the shortest distance. The shortest distance you're able to do the most quickly. But there's a few more facts you need to know. Okay, so first off, when going across the river, you can paddle 1.5 miles per hour. Okay, so that's going across the river. As you're in the water, I'll just put it this way, in the water. Okay, and then when you're on land, you're going to jog at a fast pace, or run, if we call this. You're going to do 6 miles per hour on land. Okay, so these are your two facts. So I mention this because now what might be the case is if you decide to go straight along this black path, you're going to be moving at a pretty slow rate the whole time. Maybe so slow that it would have been faster to just go straight across and then run down the side of the river. That might have been the case. Okay? Now that's actually, you could calculate that right now, I think, if you wanted to, right? Keep in mind, you know that you have distance equals rate times time. That's sort of a handy thing to know for this problem. All right. There's one more possibility, though, that you have to consider, because it is possible that maybe you'll take this green path I'm going to suggest. Maybe you'll head at some kind of an angle across the river, but not directly towards the camp. And then once you get there to this point over here on the river, then you'll head down this way along the side of the river. And maybe that's going to give us a more optimal answer. Maybe that'll save us even more time by doing that. Okay? All right, so my last little hint for the problem will be just call that distance there x. And your goal is to find x so that the amount of time it takes you to get from the starting point to the camp is minimized. And notice, if you thought about what it would mean if x were 0, that would mean, hey, just go straight across. So x equals 0 corresponds to the red path. If x were equal to 5, which would be the whole distance from this point here to the camp, then that would correspond to the black path. That means you didn't run at all on the other side of the river. You just stayed in the boat the whole time. So this variable x takes account of every case. Alrighty, so what we need to do is start coming up with some expressions for at least these distances, and then we'll be able to convert them into times using distance equals rate times time. So for example, this has to be 5 minus x. You know that because this distance over here is x, and the whole distance to the camp is 5 miles, so that's 5 minus x. So this is going to be part of my journey, this 5 minus x distance. And then I need this expression, which you can get using Pythagorean theorem. So Pythagorean theorem would tell us that this hypotenuse here would be the square root of the square of 2 and the square of x added together. So 2 squared is 4 plus x squared. So now we have both of our distances that we need to travel along. So let's keep our goal in mind here. Our goal is that we want to find the total time it takes to get down this river. Well, if you just take this formula that I suggested you consider right here, right, we can solve for t, and then that tells us that time equals distance over rate. Well, lucky for us, we know the distances we need to go. Here's one of them, and here's the other. Now, let's consider this. I'll call this like case 1. So for case 1, which is we're crossing the river, we know we have to go a distance. This time is going to equal the distance of 4 plus x squared. And then we're going to divide by that rate. But we discussed already, or the problem told us, that when we're in the water, we only go 1.5 miles per hour. So it's going to be this distance divided by 1.5. So that's the first of two cases, right? That's the time it's going to take us to get across that river. Okay. So now let's go consider the second case. Up here, this is going to be case 2. Once I get across the river, I've got to go down a distance of 5 minus x. And when I'm on land, I go 6 miles per hour. So in that case, in case 2, time is going to equal 5 minus x over 6. All right, so we can finish by saying, all right, our total time, I'll call that capital T, would just be the sum of these two things. It's going to be this thing over 1.5 plus this thing. And there you go. Now you have a formula for the total amount of time it's going to take you to get down this river. And since we have this formula, right, we can graph it and figure out where it's minimized. Now, before we go graphing, we should just talk about domain. Let's think about what x is. X is this distance in the picture here. What's the smallest x could be, and what's the largest x could be? Well, the smallest x could be would be 0, because if x equals 0, that would be the case of going straight across the river, right? And the largest x could be is x would equal 5, which is the case of going along this black path here and going across the river on the boat only and not doing any running down the other side. So our domain for this problem is going to be, we can write it this way actually, we can write it bracket 0, 5 bracket, or we could write 0 is less than or equal to x is less than or equal to 5, either one of those. So that's what we're going to do. We're going to put this in the calculator. Let's go to y equals, get rid of whatever's there. All right, so let's think about our function. It's the square root of x squared plus 4, or 4 plus x squared, and then that expression divided by 1.5. You notice I put the divided by 1.5 outside the radical. It's easier on a T89. If you type it into T89, you can get to see what it looks like. And then plus, open parentheses, 5 minus x, close parentheses, divided by 6. Okay? So there's our function. It's typed in. Okay? And then before we go graphing it, we should hit window. And this calculator, press window on a T89. Do diamond F2 to get that. You'll have 0 for x min. Make sure you have 0 there. For x max, you can go with 5. Now, for y min and y max, you never really know how to start these problems off. So I'm going to recommend just to start with negative 10 to 10. We're not sure what's going to be good yet. Let's do that to start, and let's take a look at the graph. So here's the picture. And from the look of it, look at the large screen over here. From the look of it, it looks like it doesn't really have a minimum. It looks like it's climbing the whole time. So if you press trace, so there's a trace button here on a T89, you press F3, type 0, enter. And you'll see that if x is 0, which means we go straight across the river, it takes us a time of 2.167 hours. Okay? So the question is, can we do better than that? We'll hit the right arrow a little bit, and what you notice is that y value actually starts to get a little bit smaller. Right? Now I'm down to 2.13 hours, 2.13, 2.127 hours, 2.125, 2.124, and then 2.124 again, and then 2.125. So somewhere around here, there was a minimum. It's just it was very, very slight. I couldn't tell. So according to this function, it's telling us don't go straight across. It's saying actually you're going to go some distance x. It looks like we're at x equals about 5.58 right now. So it'd be nice to have a better picture of this. And if you change your window, you can do that. So you can see we don't need to go all the way down to -10, and we certainly need to go all the way up to +10. I'm going to go back to window. I'm going to go to Ymin and Ymax. And I'll just speed up the process. I'll tell you, here's some good numbers. Try 2 for Ymin, for Ymax, that is, I'm sorry. 2 for Ymin, and do 2.5 for Ymax. And then this will actually be pretty good. Press graph, and you'll see it dip. Well, isn't that exciting? So now you could actually see that there's a minimum. So a lot of these problems are going to be about picking the right window. Okay? So let's say we hit trace again. We thought around 0.5 we had a minimum. So if we hit enter, 0.5 enter, you get the 0.2124. If you move a little bit to the left, you'll see that those y values go up. If you move a little bit to the right, they'll go down first towards the minimum, and then they start going back up again. So now you can see the x values that we're between is somewhere between 0.3 and 0.7. So you can do second calc. It'll say go to minimum, number 3. And it's going to say left bound. You can just type 0.3, enter. And then right bound, 0.8, enter, something bigger than it. And it'll look between those two numbers. It says a guess. I'll just ignore that. And here you go. So we know is the minimum time will be 2.124 hours. It'll happen when x equals 0.516 miles. So we have a min of 2.124 hours. And it's going to happen when x equals 0.516 miles. So if we go back to the picture for a second, you can actually get a sense of what that looks like. So here, back on the picture, what that's telling us is, well, make this distance 0.516. So in reality, what we end up doing is something like this. Instead of going straight across, we go at an angle such that this distance here is 0.516 miles. Okay? And then we do the rest of the trip here. And supposedly our total time at that case is going to be 2.124 hours if we do that, which is the minimum we see on the graph. Just back to this, to the calculator and so forth, this 0.516. Sometimes people do things like this. They'll go look at the table. So if you do second graph, you go to the table, and you'll notice here, x equals 0 is 2.167, x equals 1 is 2.157, and then x equals 2 goes back up again, right? So you know somewhere in there was a min. It might be between x equals 1 and x equals 2. It might be between 0 and 1. So when this happens, this sort of disadvantage of counting by ones, you have some options. If you do second window, you can go to table set, and it says table start 0, but delta table, you can change that. So instead of counting by ones, you can make it count by 0.1s. I could say 0.1, right? I hit enter. And then if I do second table, now my table is counted by 0.1s, and I could see a little bit more about where the min might be occurring here. Well, it looks like here we go. We get the minimum around 0.5, and then it goes back up again around 0.6. So you get a better sense. Either way, though, what you notice is all the y values in that y column are around 2.1 something. So when I pick my Ymin and my Ymax for my graph, and I actually pressed my graph, that's right, I picked my y value between 2 and 2.5 because I knew all my y values were in there. Okay. All right, thanks for watching.